Welcome to the problem of the week for week 6. We're going to be discussing the coaxial cable. We're using Laplace's equation to find both the potential and the electric field. So we're starting here with a coaxial cable. This is going to be a metal cylinder. The inner one has a radius A, the outer one has a radius B. They're infinite in extent in the z direction, and there's a potential V sub A on the inner cylinder and a potential V sub B on the outer cylinder, and our goal is to find the potential in between the two cylinders and also to find the electric field. Now, one thing to keep in mind, because the cylinder is infinite in extent, there can't be any z dependence to the potential, and thereby also no z dependence to the electric field. Similarly, because it's rotationally symmetric, there can be no theta dependence either. So where do we start? We're going to be looking at Laplace's equation, so let's make sure we write down Laplace's equation in cylindrical coordinates. You've been working on this during this week in understanding how Laplace's equation can be expressed in different coordinate systems. We have the first term, which involves the derivatives with respect to r, 1 over r d by dr, r d phi by dr, plus the terms that have derivatives with respect to theta, 1 over r squared d squared phi d theta squared, plus the terms with derivatives with respect to z, d squared phi dz squared. Now, of course, we know there's no z dependence and there's no theta dependence. That means the last two terms are both equal to 0. So we can simplify the equation to just having the first term with the derivatives with respect to the radial coordinate equal to 0. Now, if you look closely, what this says is the derivative of the thing in the parenthesis is equal to 0. That means the thing in the parenthesis is equal to a constant. So we'll write down the thing in the parenthesis is equal to a constant, and then we bring the r over to the other side by dividing by r. And if you like, we move the dr over to the other side as well. And then we can integrate that. And we find that phi is going to be the integral of c over r dr. Well, the integral of 1 over r is just equal to a logarithm plus a constant. So we finally determine that phi of r is some constant c times the logarithm of r plus another constant that we'll call c prime. That is effectively solving Laplace's equation. Now what we have to do is we have to put in the boundary conditions to make sure that our system satisfies the results that the potential on the inner cylinder is equal to V sub A and the potential on the outer cylinder is equal to V sub B. So we explicitly write down what those boundary conditions are. We evaluate phi at A. That's going to be C log A plus C prime, and we set that equal to VA. We're going to evaluate it at B. That's going to be C log B plus C prime, and we set that equal to VB. And now we have to solve for these. And this might look a little formidable, but when you first look at it, you can recognize that if you subtract the two, you're going to get C times log A minus log B, but that's just C times log of A over B, and that will equal VA minus VB, and I can immediately solve for C. I get C as VA minus VB over the logarithm of A over B. Now I'm going to take that result for C and plug it into the first equation and solve for C prime. And when I do that, I find C prime will equal VA minus C log A, and C was just equal to VA minus VB over log A over B. And so I get this long expression for C prime, and now I'm going to plug both C and C prime into the result for phi of r to get the expression for phi of r. So we get that phi of r is equal to VA plus VA minus VB over log A over B times the logarithm of r over A. And that comes just by substituting the C and the C prime into these equations and recognizing that I can collect the terms with the log r and the log A in them and combine them as log r over A. Okay, so now we have this nice formula for phi of r. Let's verify that it really is correct. If I substitute in r equals A, log A over A is equal to log of 1, which is 0, and I just get phi of r is equal to VA. On the other hand, if I substitute in r equals B, I get log b over a. Now log b over a divided by log a over b. Remember, log a over b is log a minus log b, and so log b over a is log b minus log a. You see that that ratio is going to be minus 1, and so I'm going to get va plus va minus vb times minus 1, so that becomes va minus va plus vb, and that indeed equals vb. So we find that this potential is satisfying the results on both boundaries. It is equal to va on the inner cylinder, and it's equal to vb on the outer cylinder. Now onto the electric field. We have to recall that the electric field is minus the gradient of phi. The field is only going to be non-zero in the radial direction because phi only depends on r. So we get the component of E in the radial direction is minus VA minus VB over log A divided by B, multiplied by 1 over r, because the derivative of log r is just 1 over r. And that's it. We've now solved the problem. And one has to remember when one is solving Laplace's equation that you really have to take this cookbook approach. You have to just follow each step. In general, each step is not all that hard, but as you amass step after step after step, you can get sometimes some long and complicated expressions, but in many cases they're still relatively simple. It's just that you have to follow your nose, make sure you go through everything correctly, and properly work out what the expressions are. So I hope that you've enjoyed following how we solve Laplace's equation for the coaxial cable.